5 and 6 both of this particular course, that is phase transformation in materials. So in the previous lecture, we have talked a lot of things, and those things are basically in form of plots, graph. That is basically free energy per mole with respect to composition, right? We have seen a lot of things like the moment we add a particular component into a pure component, what happens basically? The free energy changes, the stability changes, right? And this changes is brought by this basically entropy concept. When the moment you add a particular component into a pure component, the entropy is getting changed. That's why the free energy is also getting changed. And also we have seen that by adding particular component into a pure component, either it forms mechanical mixture, or it form a solid solution. We have seen that. Also we have seen the free energy per mole versus composition curve for a mechanical mixture and for a solid solution. And we also got the answer that basically solution are more stable, because their free energy is decreasing to a large extent the moment they're forming a solution. When you mix two component A and B, and if they form a solution, so their free energy is getting decreased, right? But for mechanical solution is not happening much. And also we have seen the tangent to the free energy per mole versus composition curve. That will basically give you the chemical potential concept, right? Because that particular tangent will cut pure A and pure B, and that will show you the chemical potential of pure A and chemical potential of pure B in that particular solid solution, right? And also we got to know that uh, if chemical potential of the component will become same in two phases or in all phases, that means it is a stability condition. Finally we got that conclusion. And also we have talked about, I remember, like if we have two different phases, or two different solid solution, and you are drawing the plot of free energy per mole versus composition in a single graph basically, then we can go for a common tangent, and that common tangent will intersect both the phases, that particular composition, that is giving you equilibrium composition basically, huh? And that okay, fine. And also that shows basically the same in chemical potential of that particular component in two phases. Okay, so today's lecture are like this, that is significance of chemical potential in phase transformation. So we talked about what is chemical potential. Chemical potential, if you remember, it is the potential or the ability of the component in the phase to take part in the chemical reaction. That means if that particular component have higher chemical potential, it has a higher ability to take part in the chemical reaction or in the reactions, right? That means if reaction will be happening, phase transformation will be happening. That is the main concept, right? Or in other way, some people can say like, that means free energy is available to do some work if chemical potential is high, right? And the next content is the delta G mix. Okay, that is free energy of mixing for the formation of solid solution at a composition of X. Okay, then free energy of mechanical mixture G, free energy of solid solution, that is G solution, then configurational entropy, then free energy is a function of various variables. We'll see that and its expressions, and derivation of Maxwell equation. I think most of the things you have already covered in your like thermodynamics and kinetics part course. Okay, again we'll see that today. Okay, so first topic is significance of chemical potential in phase transformation. So you already know the definition of chemical potential and you understand what is chemical potential exactly, right? So what is the conclusion actually? The conclusion is, for phase stability, chemical potential of the component must be equal in all phases. So you have to remember, this is most important part, that suppose you have two phase, alpha and gamma, right? Then if a component is present A in alpha phase and gamma phase, and that particular component A have same chemical potential in alpha phase as well as in gamma phase, that means that is the stability condition. Okay, suppose you have three phases, suppose alpha phase, beta phase, and gamma phase, right? And the same component A is present in alpha phase, beta phase, and gamma phase. And if you measure the chemical potential of A in alpha phase, beta phase, and gamma phase, and it is coming out same, then it is the stability condition or stability criteria, right? And the point is, if the chemical potential will be different, then what it means? It means phase transformation can happen now, right? Obviously, because it is not the stability condition, phase is not stable, it will undergo transformation if chemical potential will be different, right? And another important point you have to remember, composition equality is not the condition of stability. Listen it carefully. Stability condition is chemical potential of the species must be same. That is a stability condition. But if composition will be equal, it doesn't mean it is showing stability condition, right? Suppose A is present in alpha, A is present in beta, right? And composition of A is same, composition B is same. It doesn't mean that it is the condition of stability. Condition of stability is given by only the chemical potential. So chemical potential equality will give you the stability condition, not the composition equality. Okay. I think you people have understood up to this.
Yes, sir.
Okay, fine. You people have seen, I mean, in the movies also, like you have seen, maybe you have seen, some of you may have seen in the real situation, I don't know. If you go to this very cold oceans, huh? Like you have seen the icebergs floating on the seawater, right? So basically what happens, the seawater temperature is lower. Oh, sorry, the seawater temperature is higher basically compared to the icebergs. Then why these icebergs are still floating in the seawater? Why they are not getting melted? The iceberg should melt into the seawater because the seawater temperature is higher, but the iceberg have lower temperature, right? Why these icebergs are not melting, but they are floating? Right? You have seen the Titanic movie, right? Okay, there is a collision between the Titanic ship with the icebergs, and failure occurs, and lot of people died, and the ship got also sink, right? Anyways, so the question is why these icebergs are not melting into the seawater. Again, the concept of chemical potential is coming here. At the interface, actually at the interface of the iceberg and the seawater, the chemical potential is same. And you understand, I told, if chemical potential will be same, then there will be no phase transformation. But if there will be a difference in chemical potential, maybe there will be phase transformation. The icebergs may melt into the seawater, right? So this is happening because of presence of salt in the seawater. I told you many times, if you add a component into the pure substance, it may be a pure compound or it may be a pure element, the free energy will change or the chemical potential will change, maybe, right? So due to presence of these salts into the seawater, this dissolved salts changes the chemical potential of the seawater, right? And at the interface, the chemical potential is same, right? So that's why, since the chemical potential is same, there is no phase transformation, right? The phase transformation means the solid is not becoming liquid. The iceberg is the solid H2O, it's not becoming liquid H2O. Is okay? Now these are the three images. This is the figure 1, this is figure 2, and this is figure 3. Fine. I will explain the figure 1, 2, and 3. Already I have explained this one, but still I will explain this. You just can see this is again free energy per mole in the y-axis, and in the x-axis we have composition. So this is pure component A, this is pure component B, and when you mix A and B, and you got a support phase alpha, and this is the free energy per mole versus composition of alpha phase, you can see, right? And these red dots are showing mu naught A, and this is showing mu naught B. Mu naught A and mu naught B are nothing but the chemical, it is basically the free energy per mole of pure components, A and B. And you have taken a composition X, and at that particular composition X, this is the free energy of the alpha phase at that particular composition, okay, Gx. Okay, fine. Then this is the figure number 2. You can see the same figure, but there is a straight line. There is a red line touching this pure components free energy. Okay, so this is nothing but, you remember what is this? This is showing you the free energy per mole versus composition plot for a mechanical mixture. If A and B are forming a mechanical mixture, there is no atomic mixing, then this is the free energy curve, right? And this plot is showing you, and you understand, and this inverted parabola is for the solid solution, or for this particular phase alpha, and this straight line is the free energy curve for the mechanical mixture. So this is the mechanical mixture free energy curve, and this inverted parabola is the free energy curve for the solid solution, right? And in this figure, the same figure is here, but there is a arrow mark, you can see, and you have taken a composition of x. So at this x composition, there is an arrow mark from this straight line to this inverted curve, right? At this particular composition x. So what is it showing? It is showing you change in free energy of the mixing, del G mix, right? Because this point will show you the free energy per mole versus composition at x composition of a mechanical mixture, and this point will show you the free energy per mole versus composition value for the solid solution. So this gap is nothing but the change in free energy, delta G mix, right? So this is the del G mix due to formation of the solid solution. Okay. Now we'll see the mathematical expression. We'll see the expression for free energy of a mechanical mixture and free energy of a solid solution. So we have two components. One pure component is A and the pure component is B. When we mix them, either it will form a mechanical mixture or it will form a solid solution, right? So when A and B mix to form a mechanical mixture, what is the free energy? And that free energy is given by G only, right? You can write G mechanical mixture, or you can simply write G. Same thing, right? So what is this? G, so free energy of the mechanical mixture of A and B is equal to G naught A into 1 minus X plus G naught B into X, right? So G naught A is nothing but the free energy of the pure component A, and G naught B is the free energy of the pure component B, and this X is nothing but this mole fraction of B. So obviously the mole fraction of A will be 1 minus X. So in other way, I can write G is equal to G naught A XA plus G naught B XB, where XA and XB are the mole fraction of A and B, and G naught A and G naught B are the free energy of the pure component A and B respectively, right? Which already it is written over here. Okay, anyways, now what is the expression of free energy of the solution, which is formed by mixing of A and B? When you mix A and B and they are forming a solution, what is the free energy expression? So that expression I can write G solution, free energy of the solution of A and B, is equal to initial free energy of the mechanical mixture plus free energy of the mixing. You have to remember, this is very important. When you are mixing A and B and they are forming a solid solution, then free energy of the solution will be summation of free energy of the mechanical mixture plus free energy of the mixing, right? Free energy of the mechanical mixture, already you have written this one, right? This is the free energy of the mechanical mixture, right? Which is nothing but G, I have written. So G plus delta G mix. So delta G mix is nothing but the free energy of the mixing, and G is the free energy of the mechanical mixture. So I can write delta G mix, which is come due to mechanical mixing of A and B atomically, and G solution. So okay, fine. I can write G solution is a G plus delta G mix, which is I can write G plus, I can write delta G mix means delta H mix plus T delta S mix, right? We know this expression. Delta G is equal to delta H minus T delta S. So that's why delta G mix become delta H mix minus T delta S mix, right? So now G solution further can be written as, instead of G, I can write this expression, right? So G naught A 1 minus X plus G naught B X plus delta G mix minus T delta S mix. So this is the free energy of the solution. Okay. It is okay up to this?
Yes, sir.
Yes, sir.
Okay, fine. So we have seen that the moment we are mixing A and B and it is forming a solid solution, then the free energy of the solution will become the addition of free energy of the mechanical mixture plus free energy due to mixing, right? And free energy due to mixing is nothing but the formula of delta G, right? Delta G is called delta H plus T delta S, fine? But mixing term will be there, right? So now there is condition. Suppose you mix A and B and they form a ideal solution. And you people understood if two components are forming ideal solution, then delta H mix will be equal to zero. You people know this thing, right? Or heat of mixing, change in heat of mixing is zero, or change in enthalpy of mixing will be zero, right? You people know this thing, right? From the thermodynamics. So the expression will change, obviously. If this is the situation, the initial expression G solution, this one will be getting changed because this delta H mix will be zero, right? So you simply can write G solution. That means this G solution means the solution of the ideal solution. G ideal solution. So G ideal solution will be equal to G naught A 1 minus X plus G naught B X minus T delta S mix. That means in this expression, delta H mix will be zero because this is the free energy of the ideal solution. Okay. And we know we have two types of entropy. Now, you people remember already from the earlier lectures, we can have two type of entropy. One entropy will come due to vibrations, lattice vibration of atoms, molecules, right? And that is due to change in temperature. If you change the temperature, if you increase the temperature, the vibration will be more and more and more. So that is actually entropy, that is called thermal entropy, entropy due to vibration, or some people call vibrational entropy, right? And another kind of entropy will come into picture if you are having alloy or a mixture, right? You do not have any pure component. Because of addition of more components, more entropy will come into picture. That is called configurational entropy. Because more component means more number of arrangement can be possible. More is the arrangement possible, more is the configurational entropy, right? So we can have two type of entropy, vibrational and configurational, right? So basically, when we are talking about solutions, basically solid solutions or liquid solutions, in that condition we take this vibrational entropy negligible. We don't consider vibrational entropy will be there. We basically consider configurational entropy in that condition, right? But whenever we are having pure substances like pure metals, pure elements, pure compounds, there we basically consider the vibrational entropy. But when we are not talking about pure components, impure components or alloy or solutions like that, or combination of more compounds, there we are considering configurational entropy, because more number of arrangement may be possible. Okay, here I have written already S. So S is the combination of thermal entropy, S thermal plus S configurational. And we also can write S is equal to S configurational because we are this thermal entropy is negligible. Okay, so I can write del S is equal to del S configuration, right? Del S configurational entropy. Okay, so configurational entropy expression already we know from the earlier class. It is del S configuration will be K log omega or K log W. Anything you can write, K log omega or K log W. Log means here you have to write ln basically. K, if you remember, is Boltzmann constant, and this omega is nothing but the number of microstate for a given macrostate. Your macrostate may be fixed, but you can have lot of microstate, right? Similarly, if you want, you can have lot of macrostate also. But if you carefully look at the microstate will be very, very high. Macrostate means it is a higher term, big term. But microstate means it is small term, but number of small term will be more and more and more. Suppose you can try this. Suppose you have two dice, for example. You take two dice, dice of the Ludo. You people play Ludo. I know that. So if you if you take two Ludo and you want that you may have lot of macrostate, for example. lot of macrostate can be possible, like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Up to 12 you can go. You have two dice. You are playing with two dice, for example. So you can get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Up to 12 you can reach. So 2 is one macrostate, 3 is one macrostate, 4 is one macrostate. Like this, you have up to 12 you can have macrostate, right? So for getting those macrostate, you can have lot of combinations. You can have lot of combinations. You can have lot of probability, right? To getting 2, getting 3, getting 4, getting 5 out of these two dice, right? So if you carefully look at the macrostate 7, you can have lot of probability to get this 7. So number of microstate will be higher for this 7 one, right? You can compare. You can try this. Anyways, so what I mean to say is, now I want to show you the delta S configurational entropy. So configurational entropy can be written as negative Kn XA ln XA plus XB ln XB. Okay, we can write like this. Further, I can write, instead of this XA and this XA, you remember what is XA and what is XB. XB is X only, but XA is 1 minus X, right? We have taken that already. So instead of XA, you can write 1 minus X. Instead of XB, you can write X. So you can further simplify this equation, and you can finally see free energy of the solution is Z naught A 1 minus X plus Z naught B X plus T Kn this much. 1 minus X ln 1 minus X plus X ln X. So this is the final expression of the free energy of solution. What I have done, I have simply substitute what? I have simply substitute del S mix instead of del S configuration. You should not be confused. Del S mix is nothing but del S configuration. Okay, configurational entropy. And configurational entropy expression is this one, right? So this part is only for your mechanical mixture, you have seen, and this part is for your del H mix. And you have taken, sorry, del G mix. So del G mix, del H mix is already 0. So we have only this much, you have seen. I'm going to the previous slide. This was your expression, right? G solution is equal to, this is the mechanical mixture free energy, and this is the free energy of the solution, where del H mix is 0, right? So same thing I have written in. So instead of this del S mix, I have taken del S configuration. And del S configuration, already we have seen what is del S configuration. Okay. So finally, so this is the final expression. Just have a look. This is the final expression. G solution is equal to G naught A 1 minus X plus Z naught B X plus RT 1 minus X ln X 1 minus X plus X ln X. So this is the final expression. Okay. So this part you can simply say T into del S configuration from here to here. Now if you carefully look, this part is kind of straight line equation, right? This part is kind of straight line equation, and this part is kind of parabolic equation, right? Okay, the second part is kind of parabolic equation term, and this part is actually, first part of this equation is kind of straight line equation, right? So what you can write, so above is the free energy of the ideal solution of A and B. Now G naught A 1 minus X plus Z naught B X is the equation of a straight line, and if X is the fraction, then ln X is equal to 1 minus X, and ln 1 minus X is equal to X, right? So G ideal solution will be this much. So from this above equation, the first part of the equation is a straight line, and the second part of the equation is a parabolic equation, which I already told you. This part of equation is parabolic equation, and this part is a straight line equation, right? And you have seen already, huh? This one. This is a straight line, which is due to mechanical mixing, and this is the parabolic, which already you have seen. Okay. Now, free energy is a function of what, basically? I told you many times, free energy is not constant, you have to remember. Free energy depends upon temperature. If you change the temperature, free energy will change. Similarly, if you change the pressure, free energy also changes. And if you change the composition, free energy will change. You have already seen those things, right? Basically, in maximum case, we take atmospheric pressure. So 1 atmospheric pressure. So free energy is only function of temperature and composition. In the phase diagram, we basically used to see like that. We keep the pressure constant, 1 atmospheric pressure, and we only change the temperature and composition. So obviously, if temperature changes, free energy changes. If composition changes, free energy changes. That's why we have different phases at different composition and at different temperature. You people have understood now? That's why if you change the temperature, the free energy will change, means the new phase will come out maybe. Initial phase will not remain stable, right? Similarly, if you change the composition, free energy will change. So by changing the composition also, you have different phases. One phase will not remain stable. Okay. So free energy is a function of, I can simply write, so free energy G is a function F of T temperature, function of P pressure, function of X composition. So free energy is a function of temperature, pressure, and composition. Okay. So if we take differential of this free energy G, we can write like this: dz. This is a differential form. Differential form of this G. Dz is equal to partial differential of dz by dt, where pressure and composition is constant, dt, plus dz by dp, where temperature and composition is constant, dp, plus dz by dx, where temperature and pressure is constant, dx. You people have understood up to this?
Yes, sir.
So I told free energy is a function of temperature, pressure, composition. Now I want to find out the differentiation of this free energy, dz. So it will be obviously partial differential of this all temperature, pressure, and composition. So if you are taking temperature, then pressure and composition will be constant. If you are taking pressure, then temperature and composition will be constant. If you are taking composition, x, then temperature and pressure will be constant, right? So you can write like this kind of, these are the partial differential of this, right? So further I can write, this is very interesting, just have a look. Now I can write this part, first part, dz by dt when pressure and composition is constant. I can write like this, minus sdt. Okay. Instead of this, I can write minus sdt. You know these expressions from the thermodynamics, right? Similarly, when there will be dz by dp, where temperature and composition is constant, dp, you can simply write bdp instead of this, right? Similarly, when this is the situation, partial differential dz by dx when temperature and pressure is constant, dx, we can simply write mu dx. Mu is the chemical potential, right? So your temperature is related to entropy, your pressure is related to your volume, and your composition is related to chemical potential. It is okay up to this?
Yes,
Okay,
sir.
so you can write finally dz is equal to minus sdt plus bdp plus mu dx, where mu is the chemical potential, v is the volume, and here s is the entropy. Okay, so here dt is here, dp is here, and dx is here already. Fine. So this is the final expression. So when somebody will ask to write an expression in differential form of free energy, so you can write dz is called minus sdt plus bdp plus mu dx. So it shows that free energy is a function of temperature, pressure, and composition. Okay. So now it is written, if many number of components are present in the solution, then what you can write? So you understand, if many number of components will be present, then your mu will be getting changed, chemical potential will getting changed, and this x will getting changed, right? So what you can write, dz is equal to minus sdt plus bdp plus summation of I is equal to 1 to n mu I dxi. Okay, I is the number of components. Fine. In this way you can write. But if you have single component, you can simply write mu dx. But if you have more number of components, you can write summation of I is equal to 1 to n mu I dxi. Okay, so dz is equal to minus sdt plus bdp plus summation of I is equal to 1 to n mu I dxi. Okay, so this above equation is the free energy change of solid or liquid solution. Okay, I think this kind of expression we have seen in thermodynamics also. Okay, so we know that. Okay, fine. Now you people all know the Maxwell equation, famous Maxwell equation. That is dz is equal to bdp minus sdt. How to derive this? So I'll go into the derivation part. So to derive this, you have to use the first law of thermodynamics, second law of thermodynamics, right? Then you can easily derive. And you should know the different functions. Thermodynamics function, enthalpy, your internal energy, entropy, right? So you can see I want to derive Maxwell equation, which is dz is equal to bdp minus sdt. So what I can do, I can simply write g is equal to h minus ts. So similarly, I can write dz is equal to dh minus tds minus sdt, obviously, right? Since g is equal to h minus ts, if you take differentiation, then it will be d. You can write dh is equal to, dz is equal to dh minus tds minus sdt. Okay. Similarly, you can write h, instead of h, you can write u plus pb. We know that, right? H is equal to u plus pb. So this dh means d whole bracket u plus pb, right? Minus tds minus sdt. Similarly, you can write here u plus pb means you can write du plus pdv plus bdp, right? This is du plus dpb or pdp, same thing you can write, huh? So du plus pdb plus bdp, and here minus tds will be there and minus sdt will be there, right? Similarly, you can write this expression. After this expression, you can write delta q plus bdp minus tds minus sdt. From the first law we know these things. Okay, that means instead of du plus pdb, you can write delta q. Delta q is equal to du plus pdv. Okay, this is the first law of thermodynamics. Why I have written del q? Can you tell me why I have written dq here? Like I have written du plus pdv plus bdp plus here I have written du. Why I am not writing here dq? I'm writing
Path
del q.
function queued.
Path function.
Path function.
Ah, very good. You remember. Very good. This is a path function. Heat is a q is nothing but the heat. Heat is a path function. But internal energy u is a state function, right? Pressure, volume, those are state functions. Okay. Anyways, so instead of du plus pdv, you can write del q, because del q is called du plus pdv from the first law, and other expressions are remain same, minus tds plus minus sdt. Okay. So now you can see here, you can write tds plus bdp. Okay, fine. This expression del q, from the second law we know that del q is equal to tds. You remember the expression, this one?
Yes, sir.
Because we know that ds is equal to del q by t. Is it correct?
Yes, sir.
Yes,
Right.
sir.
So similarly, we know that del ds is equal to del q by t. So obviously, then if ds is equal to del q by t, then del q is equal to tds, right? So instead of del q, you can write tds, right? Then other expression will remain same, bdp minus tds minus sdt. Now you have common terms. This is positive, this is negative. So positive tds, negative tds will cancel out. So you left with bdp and on minus sdt. So you can write dz is equal to bdp minus sdt. So this is the Maxwell equation, right? You have to remember. So free energy depends upon volume and this entropy. Okay. So now, okay, now if we want to know the stability conditions for the solid solution, then change in free energy dz must be 0. Okay. So you have to remember, if you want to know the stability condition, then for the solid solution, then change in free energy, dz must be 0, right? Change in free energy should be 0 for the stability condition. So you can write dz is equal to minus sdt plus bdp plus summation of I is equal to 1 to n mu I dxi is equal to 0, right? We have derived this expression, this one. When free energy is a function of temperature, pressure, and composition, right? So that will be equal to 0. So now solving this equation solving is not so easy. So we can use a graph to solve this. So we can use a graph. You can see this is the plot, free energy per mole versus composition axis. You have pure component A here. You have pure component B here, right? And this is mu naught, mu A naught. This is mu B naught, or mu naught A, mu naught B. These are the free energy of the pure component A, pure component B, right? And this is the free energy per mole versus composition curve, right? And this straight line, you remember, this is for the mechanical mixture free energy, and this inverted parabola is for the solid solution free energy, right? And you know the tangent. This is the tangent drawn at a composition of x, right? At this particular composition of x, this is the tangent drawn, and this tangent will intersect the pure component A and pure component B. That will give you the chemical potential. So this is the chemical potential of A, this is the chemical potential of B. Since it has a composition of x, and since it has a composition 1 minus x, it is given here, right? And at this point you can have a free energy, that is Gx. Okay, so mu A 1 minus x is the chemical potential of A in the solid solution having 1 minus x mole fraction of A, and mu Bx is nothing but the chemical potential of B having x mole fraction of B, okay, in the solid solution. So now stability criteria, which we want to discuss. So stability criteria is very simple. I told you this is mu A alpha is equal to mu A gamma. If you have two phases, alpha and gamma, then you have a component A. That particular component have a same chemical potential in alpha phase and gamma phase, right? Similarly, another component is B. So chemical potential of B in alpha phase should be equal to chemical potential of B in gamma phase, right? So now if you want to draw a plot, this plot is showing free energy of alpha and gamma with respect to composition. So again, in y-axis you have free energy per mole, in x-axis you have carbon, suppose concentration of carbon. Why concentration of carbon? Because we are considering mild steel here. Okay, one component is iron, one component is carbon. Okay, so percentage of carbon we have written here, right? So you can see this is the free energy curve for alpha phase, alpha solid solution, and this is the free energy of gamma phase or gamma solid solution, right? And we have taken a temperature which is T1. And this is a common tangent. If you remember, we can draw a common tangent which will intersect gamma and alpha, two different solution at a point. And this particular point is called what? Anybody remember? Where this common tangent will intersect this particular composition is called what? This point and this point. It is called equilibrium composition, if you remember, right? Yes, this is called equilibrium compositions. Well, and since this is a common tangent to both phases, that means, and this tangent will intersect pure A at this end and pure B in this end. And if you remember, pure A side will give you chemical potential of A, and pure B side will give you chemical potential of B. But this tangent is intersecting two phases, different phases, alpha phase and gamma phase. That means this particular point will show you chemical potential of A in alpha phase is equal to chemical potential of A in gamma phase. Similarly, this point will show you chemical potential of A in alpha phase, sorry, chemical potential of B. This is the B side. So chemical potential of B in alpha phase will be equal to chemical potential of B in gamma phase, right? So now this is the equilibrium condition or stability criteria. Okay. Okay, I will stop here. You can stop the recording. Okay, please take the screenshot